Good morning, everyone. We want to take a look at the question this morning. It's interesting. Now, a client called you and he said he has the following information that you should design a solar system that will fit in for him. How do you raise the quotation for him? That's what we are looking at today. Now, he has the following items. Number one, total load is 2 kilowatts. Number 2, 3 kVA, 48 volts. Number 3, 3 kVA, 24 volts power inverter. That is what he has in his house. Now, we want to look at what should come into your mind as the first thing is that what is the size of the solar battery to use if this client is to run this system for 13 hours. This load of 2 kVA kilowatts, he wants to run it for 13 good hours. What is the size of the battery? That is question A. Question B. If the inverter you are using is 3 kVA 48 volts with a total sum of 5,000 watts solar panel with each 460 watts each of the panel, and if the inverter you are using, that is B2 now, inverter you are using is 3 kVA 24 volts with the total sum of 2000 watts solar panel of each 200 watts. Now, the question number 1 under that B, draw the block diagram of the circuit. Remember, you have 2 circuits now. When you are using 5,000 watts solar panel as the sum, 460 watts each. Then the second one is when you are using 200 watts solar panel as the total sum, 2000 watts as the total sum, and 200 watts solar panel per each. Now the question is that draw the block diagram of the circuit. Question 2, what is the total output current? Question 3, advise the client on the types of charge controller to be used and their specifications. Question C, how many pieces of the solar battery do you need on this system if you are to use 200 amps lead acid battery, or you can put it tubular battery? How many pieces of the battery do you need to use? Question D, draw a well-labeled block diagram of a solar system with a hybrid inverter using an external charge controller. So this is where we are going to end the question for today. Now, we want to look at it. Actually, this question can come to any installer. The owner of the inverter, the client as well, can benefit from this question. In case you have the total load you have in your house, how do you approach the items that you needed is important in this question, and we are going to highlight them, and you will understand it as you follow us to the end in this class. So, question number 1. Question number 1. What is the size of the solar battery to use if you are to run this load for 13 hours? What is the size of the solar battery you are to use if you are to run this load for 13 good hours? 13 hours, you have to run this load for 13 hours. That's question number 1A. Question number 1B. if the inverter you are using is 3 kVA 48 volts with the total sum of the solar panel 5,000 watts, and each of the panel of the 5,000 watts is 460 watts, and with another set of solar panel the total sum is 2,000 watts, with each of it is 200 watts. Now, question number 1. Draw under this B now. Draw the block diagram of the circuit, which is what will guide you. Draw the block diagram of the circuit. 2. What is the total output current? 3. Advise the client on the type of charge controller to be used and their specifications. That is under question B. Now we go to question C. How many pieces of the solar battery do you need on this system if you are to use 200 amps lead acid battery? D. Draw a well-labeled diagram of a solar system with a hybrid inverter using an external charge controller. So we want to look at it now so that we take it one after the other. Question 1A. What is the size of the solar battery to use if you are to run this load for 13 hours? And remember that the size of the battery is the capacity of the battery. And that is why we are looking at it. So now, the battery capacity. The battery capacity is equal to what? Battery capacity is equal to total load times what? The running hours. Times the running hours. That means the battery capacity is equal to what? The total load we have is 2,000 watts. Times the running hour is 13 hours, which is equal to what? 26 watts hour. 26,000 equals to 26,000 watts hour. The total load given is 2,000 as I earlier said. Then the running hour is 13. And as I've solved it on the board, we have 26,000 watt hour. So in this 26,000 is as well as equal to 26 kilowatts hour. So we move forward. So note that this is your total energy consumption per day. Now, considering the region we are in, especially in this country, we are close to the line of equator. Our peak sun hour are considered to be 5 to 5.5 per hours per day. And that is why we are looking at the total panel that will come out if you are to go to the market to go and buy. How many panels are you going to buy of this 460 watts? And we are using calculation now to figure them out so that we will not make a mistake. And that is why we are looking at it in this direction. So the total solar panel wattage needed, your total energy consumption per day, all over what the peak sun are. And at this time, we are using the 5.5 peak sun hour. So the total solar panel the numbers of 460 watts solar panel needed is equal to the battery capacity, that is your energy consumption per day, which is what total consumption per day all over what peak sun hour, which is equal to 26,000 watt hour all over what 5.5 hour, because hour cancel hour. By the time you divide it, it gives you what? So at the end, by the time you divide it, it gives you 4.727. 4.727, which is equal to approximately 5,000 watts. So the total solar panel we have now is 5,000 watts. 5,000 watts. So the number of the 460 watt solar panel you needed, as you have gotten this 5,000, is equal to what? 5,000 divided by 460. It gives you what? 5,000 divided by 460. It gives you 10.8. It gives you 10.8. It will give you 10.8 pieces. But because there is no 0.8 in the calculation, we have to approximate it to 11. When you approximate it, it will give you 11 what? 11 pieces. 11 pieces. So these 11 pieces now, when it comes to a practical reality, we are looking at 12 because 11 is an even number. If you connect in series 3, 3, 3, it will give you 12. If you connect in series 4, 4, 4, it will give you 12. If you connect in series 2, 2, 2, it will still give you 10. So I will advise you approximate it to be what? 12. Either use 10 pieces or 12 pieces. 10 either you use 10 pieces or pieces of the solar panel. Now, you have gotten the exact numbers of solar panel under standard test condition, like you are using if you are using Jinko panels. Because where we are, the irradiance of the sun is almost half of the factory testing under the standard testing condition. And as such, I will advise, if you wish, because depends on what you are looking for you to have a maximum performance of your system, instead of using 12 to multiply it, that 12 panels, multiply it by 2, it gives you what? 24 pieces. With these 24 pieces of panel in this system, it will perform excellently well for you. Alright, now we need to draw the block diagram. The question says we should draw the block diagram of this system. So we are using 24 pieces for the block diagram now. As you can see, we want to do the block diagram, how it can be connected. So this is the block diagram of the system. Now at this time, each of this, now this is where they will put a lot of things into consideration. On that particular system, there is what we call the parameters that follows the panel count, and that is the electrical parameters under the standard test condition of the panel. The main maximum power of the panel is 460 watts. Open circuit voltage is 39. So at this time, we want to look at how many volts that are involved. Now, we see the maximum power voltage is 39 to 41. The short circuit current is 13.5 to 14.6. And the maximum power current is 12 to 13.9. The module efficiency is 21 to 23%. Then we talk of the power tolerance. It's minus or plus 5 watts. Now what we need to do is that the question said, because we are putting the voltage and the amps into consideration at this point, because the voltage, we are looking at the voltage as 40 volts per each of the panel. From the parameter, we take 40 volts per each. That is 40 volts DC per each of the what? The panel. Now, we are taking how many? That is, each of the panel is what? 40 volts. Now we have 30 amps. Per each of the panels. Now, we connect these 12 pieces of panels in series. This series connection. The output we have, when you connect in series, the voltage increases. So this voltage now, multiply this voltage by 12, it gives you 480 volts. We multiply this one too by what? 12, it gives you 480 volts. So here we have 480 volts. Here we have 480 volts. Now, because and the amps remains 13 amps. And the amps here remain 13 amps. Because in series connection, the amps remains the same. Now you bring them together to the what? Parallel connection. So at this point of you joining them together here, the voltage remains the same, while the amps increase. So we have what? Voltage remains the same. That is 480 volts. Then the amps is what? 13 plus 13, because of this parallel connection here now. We have 26 amps. So the output current of the circuit is equals to 13 plus 13 equals to 26 amps. Based on this connection that we have done, the output current is 26 amps. Since in series connection, voltage is added while current remains the same, and in parallel connection, voltage remains the same and current increases and that is the answer we have gotten. Now, we want to step to the second phase. We have used the first inverted demand has, and we have raised the quotation for that. Now, the second inverted demand has is what we want to look at now. For 2000, the total sum of the wattage is 2000 watts, and solar panels, and each of them is 200 watts each of the solar panel. So in that solar panel, the electrical parameters of the 460 watt solar panel is different from the electrical parameters of 200 watts solar panel. So note it from now, and all of them are written at the back of the panel, at the sticker on the back or at the back of the panel. So it's good you look at it so that you know how your configuration will look like. So the peak power is actually 200 watts. The voltage at maximum power is from 18 volts to 22 volts for 12 volt system, and for 24 volt system is from 36 to 38 volts. So if you are connecting it to the charge controller of 12 volts, it can go. You are connecting to the charge controller of 24 volts, it can go as well. Depends on your configuration. So current at maximum power is 9 to 11 amps for 12 volts and 5 to 6 amps for 24 volts. That is to tell you that the cells connected inside the panel recognize the parallel connection and recognize the series connection. Then open circuit voltage as well is what 22 to 24 volts for 12 volts panel system, and what 43 and to 45 volts for 24 volts system. Short circuit current is 10 to 12 amps for 12 volts and 5 to 6 amps for 24 volts. The maximum system voltage is 1000 volts. Now, it weighs and all of that. You may not go to those ones. So, for us to know the number of total panels that we needed at this time, without considering the irradiance of the region, So, for us now to update it, without considering the irradiance of the region, we have what? Is equals to 2000 divided by what? 200. So this goes. Divide this, give you is equals to what? 10 pieces. So without considering the irradiance of it, but mind you that the voltage we are looking at is what? We are looking at 36 volts, and for the voltage we are looking at is what? We are looking at 18 volts. So if each of this is 18 volts and we are connecting it to the 24 volt system, that means this system has to be rearranged Without considering the irradiance, we have so between this panel, this one has 18 volts. This one is 18 volts. So 18 volts plus 18 volts, it gives you what? 36 volts. So each of these circuits now have 36 volts. And 36 volts connected and connected in parallel. 36 volts connected in parallel. It remains what? 36 volts. Then the arms will now build together. So since we are having 9 here, this one is a 9, this one is a 9. When you connect the two together in series, the arms remains the same. So this arms is a 9, this is a 9, this is a 9, this is a 9, this is a 9. Therefore, the total output current is equal to 9 plus 9 plus 9 plus 9 plus 9 is equal to what? 45 amps. So with this total output current and the voltage for what you have gotten outside here now, so what you have here is 36 volts, 45 amps. This is what goes to your charge controller without putting the irradiance into consideration. But if you put the irradiance into consideration, automatically what you will have here you have the same automatically as you connect the voltage together in parallel here. What you have here is what you have here. So as you connect it in parallel, the amps will increase to 90 amps. The amps will increase to 90 amps while the voltage remains the same. So we have two types. Now we are looking at the now the question number B3 says, advise the client on the type of charge controller to be used and their specifications. Now we have two types of solar charge controller. Number one is PWM, that is pulse width modulation. Number two is MPPT, maximum power point tracking. I will advise that the client should use an MPPT charge controller with the following reasons. Number one, higher efficiency and power yields. This maximum power point tracking controller converts excess voltage from panel into additional current for batteries. Because it converts the excess current and send it to the battery for battery to use, it increases the efficiency up to 97.5% compared to around 70 to 80% for PWM, resulting in 15 to 30 more power gain. And this is very, very important. That is the efficiency. Now, the optimal performance at the code or when it's shaded, maximum power point tracking shines in cold temperature, and it's the power it draw the power, track more power during the cold temperature where panel voltage increases along it to capture that extra voltage, whereas PWM efficiency drops at the shading area or the cold weather. Now, number three, system flexibility. MPPT allow you to use higher voltage and high voltage solar panel, while PWM restricts you to the value of the charge controller you are using. Number four, MPPT reduce the wiring costs, allowing the higher input voltage connecting panels in series, but PWM does not allow that. The wiring cost is more for PWM than MPPT. Then number five, the last but not the least, is what? Better performance in low light. MPPT handle changes in sunlight intensity more efficient than PWM. And all these things that I've mentioned now ensure faster charging, and it supports, and MPPT also as well, it supports the large installation compared to PWM. So with these reasons, I will advise my client to use MPPT charge controller. I will advise my client to use MPPT solar charge controller instead of PWM, though more expensive, but the advantage can never be compared with the price. All right. So now we are looking at the question number C. And this question number C is actually a point of concern for you and for me, for us to make a progress. Question number C. How many pieces of the solar battery do you need on this system if you are to use a 200 amps lead acid battery? Now, remember that we have the total amps. That is question number C. Now, we have finished with question number what? B. We have question number C. Now, if you are using 200 amps solar battery, you are using 200 amps solar battery, and the total battery capacity we have is 26 kilowatts hour. Now, one pieces of total battery capacity is equal to 26 kilowatts hour, which is equal to 26,000 watts hour. Now, each of 200 amps, 12 volts, are using power formula. The power formula is P equals to IV, where P is the power of the battery. I is equal to the current. Then V is equal to what? Voltage. V is equal to voltage. So now we have the battery is 200 amps and 12 volts. Therefore, the power in the battery is equal to what? 200 times 12 is equal to what? 2,400. Watts. So we have 2,400 watts. So in this, the number of the battery is equal to 26,000 divided by what? 2,400. So this goes. You have 260 over what? 24. So the number of batteries is what total battery energy all over what? The individual energy. So what I'm saying is that the number of battery is equal to the total battery energy divided by individual battery energy. So individual battery energy is 2,400, while the total battery energy is what? 26,000. So 26,000 divided by 2,400, it gives you what? 10.8. So by this 10.8, you can now, to round it up, the system needs 10 pieces of lead acid battery at minimum. And at minimum, the system needs 10 pieces of lead acid battery. But at maximum, you can use 12. So, the solar, question D, the solar, you see that we have the grid. The picture showing under the video now, you see the answer to question D. By this side, you have the national grid. That is the AC input to the inverter. Then under it, we have the resident house where you install the solar system, where it will power the electronics of the house. Then by the right, you will see the battery and the charge controller and the panel. Just to study it. This is how it is supposed to look like as you study it. So when you execute it, it should come out and give you a result like this. Thank you and God bless you. Don't forget to subscribe so that you can follow us up. Thank you.